So let's round up the physics real quick and the construction core memory shield here. It's a kit from teamd.com. I will link it under the description. And basically you have 32 cores. Those are iron rings. These are wires going vertical and then horizontal. You can also see that the circuit is like coming in here and then out here. It's the same for all of these. That's what I tried to point out in the video. And you have another line which goes through all of them, actually. These, all that the diagonal stuff, that's one wire actually. And that wire ends up in those 2 points here, which then is routed to a comparator, LM393. And here is where any change will be picked up or induced into that wire. That's how we read if there's a 1 or a 0 on the line. So yeah, so let's get into the physics real quick. Not going to dwell so much on it because I don't really understand it 100%. So the physics, when you have a wire, a current going through a wire, and forget the ring now, you will get a magnetic field around it. So this is the right hand rule, right? You have the current going that way, then you have the magnetic field this way, like that. So if you have a ferrite core inside that wire, then this core will pick up that magnetic field. So it will affect the magnetic pole. So if it's magnetized in one direction, then you can magnetize it in the other direction. So how do you store a value? Well, actually you have to also make it able to handle half the current in the opposite direction, because you have 2 wires going in. Actually 3, the third is the sense, but in essential you have 2 wires because you have X and Y, right? Like you have to address it. So when you are addressing one core here, another core will have half the current, but the core you're addressing have a full current. So therefore you need hysteresis, because okay, let's say the ring is polarized on this side, let's say negative, and then you push half the current into that ring, through that ring, then it's not enough current or a magnetic field to flip this state. So, but if you push 2 currents through that ring, then you will change. And when you do that, if it was a 0 here, it will change state, and what happens then? You will get a little pulse out of that ring, because a moving magnetic field is able to induce a voltage in another wire. So let's have a look at that. That's very interesting. So here you can see, here they write a 1, but there's already a 1 there, so you don't get any spikes. So the spikes on the left and right side of the poles, they are just noise, so that's not actually reading anything. Here they insert a 1. Yeah, so the first 2 changed the memory state and the last one didn't. So here you can see we get a little spike. That means that the core changes state. So and that is the wire that I talked about up here, the one that goes through all of them, right, on diagonal, and then ends up into this comparator. So that's how you pick up. So now you see that you actually have to write to read, and when you have to write to read, then you lose data. So because if it was a 0 and I write a 1, then you can see that it was a 0 because you get a pulse. But then you have to put it back again. So a read has to always follow by a write. So to put the data back. So here is the construction. The thing is that, okay, this is how you address it. You have one driver driving this way and the other driver driving this way. I think it's the reason is because of the angle has to be opposite of each other to not affect each other's fields. But a more effective way of doing it is to do it like this. Instead of having a separate driver for one way and then another driver for the other way, what they do is they make a loop instead. So if your current going in here and in here is this two currents into the same course, then you're addressing this one. However, the current going out here and up here will cancel each other because there's a current coming in and a current coming out so of the ring. So that's how you save half the amount of drivers. So it's really cool. And then here is what I explained. Really nice drawings, by the way. You can see current coming in and you try to address with this line. Then you have one coming in and then one coming the opposite way, sort of. So this one will cancel. Here, the current that came in here will then return here. So then you have two currents going through this coil. So then this one will receive the full current. And what does full current mean? Let's get back here. A full current is able to switch the state. That's what it is. And the reason why these rings are so sharp, they are like square edges. The reason for that is the sharper they are, from what I learned, I don't know really why, but you get a wider S shape in your hysteresis diagram here. So that means you can discriminate between half and full current much better. Because you're only talking about like, what is it, like 20 millivolt or something of a pulse. So that's very weak. I don't think I have equipment to measure that. It will just fall into the noise of my oscilloscope, PC oscilloscope. So this is this kit. So this is a sensor. So and assembly. So we'll go through that later in the video. So here's the CPLD, then over to the Arduino program. So yeah, so schematic also, if you want to see.
I think that I is industrial, is it? Industrial rating stroke P for the plastic package. Is that SM or is that SL? I can't quite see. I think it might be. I think it's SM, surface mount. So yeah, that's very handy. It's the same chip as the one I've programmed for the rotating dot bent. Now I do have a chip puller here, but if I can't get the screwdriver under there, I'm not going to be able to get the chip puller ends under there either, so I think I'm just going to use the screwdriver. Right, that's the chip out. Now I'm going to have to put this in. Now these header pins are massively thicker than the chip pins, so is that going to distort this socket so much that... Right, out you come, little chippy. Good. Okay, now I'm going to get that in there. It's gone in. Through the floor flap, and there it is. It's sitting in there. That should do exactly the same job as that. Let's get the programming kit out. Right, I'll use this pit kit too. Let's just make sure it powers up. It seems to be that way around. Yeah, the lights come on, my computer went bing bing bong and lots of other noises. What is it saying now? Oh, we're setting up the pit kit too. Hex file, otherwise there's no hex file for the programmer to program. Right, so that looks like it's ready for programming. Right, as I remember it, this goes upside down on here. The lights come on, that's a good... okay, that's not working. Let's switch it off and on again. No, still not working. Why is that? Right, You just got to love debugging, haven't you? Because I was sitting here thinking, oh no, now I've got trouble. Now I've got problems with the fact that the clock in here, which is 8 megahertz, which I tweaked up a little bit, so it's slightly over 8 megahertz, which means that the pulse width coming out to the NeoPixel ring is slightly under 500 nanoseconds. And I thought, I've gone to this other chip, and it just doesn't quite work. But actually, it's a lot simpler than
So we have PNP and NPN, and I don't remember which is what, so but I've written down 337 and 327, and it's these two rows here. And well, have to do some digging first. But I don't think we need to find the datasheet, we just push it down here and see. This is the 337, push it down here. Hopefully, yeah, it seems to be working. NPN, so this is NPN and this is PNP. Let's just write that down. This should be PNP. Should check that to be sure. So let's see. The struggle is real, folks. Let's see. Should be PNP. Yep. Great, I trust the meter. So it's not really a good meter, but it's very good for classifying. So you can hold the button and selection. Yeah, sometimes this works, sometimes it doesn't, but this time it did work. So I haven't changed the 9-volt battery here for a long time, so this soft start is showing very little power. That's great. A problem here. So it looks like PNP and NPN, but it's not the case. So it's like 13 and 14, Q13, Q14 are PNP and NPN. So that's these two. And the problem I have now is that this is 2017 112 and this is not. So the documentation is not updated. And you can see that on the web page, that you see this is not the same schematic, but I'm guessing that these are the same So just here have changed. You can see this one is moved over here, right? And these are low profile. So anyway, I will just make it simple. I'll just take the NPN first and then PNP later. So just follow the schematic. So what are these PNP and NPN anyway? So the NPN pulls down and the PNP pulls up, as you can see in the schematic. Okay, that's another problem. I've gotten straight, right? Straight. It's not a big, it's not a big deal, but it's a little bit boring. And straight row, and here they are zigzagged. Like, anyway, it's not a big deal, just a bit annoying. So just bend one pin and then force it down. So yeah, so what it does is let's look at the schematic. I think these are connected to the cores, right? So it's possible to drive them either way. Just for the record, if anyone is following, actually I pushed it down at 13 there, but it's 14 is NPN, right? It's because I was talking at the same time when I do this. Now I'll turn the camera off and just do it. So that was all the NPN, and it wasn't that hard really, just even numbers, right? And all the odd numbers, they are PNP. Yeah, but I forgot to say that this push-pull is drawing power through these lines, wires, and they go through the cores. So if one current goes through them, it's just half the current needed to actually flip them over if they are in the opposite state. Then the opposite magnetic polarity, then the current, then the polarity caused by the current through the wire. Sorry for the difficult explanation. And yeah, so if there are two currents at the same time, then it will be enough to flip the polarity. So that went rather well, no problems really. The only issue I had was the schematic doesn't match the numbers on these resistors, so but they are very close. So there's like 1.8k versus 2k and such like that. So another reason why I have delayed this project is because I need the Arduino. So yeah, so here it is. So it's supposed to fit right in there. So probably will be a bit difficult at first. Let's try it again. Yeah, so I have to program it, the Arduino, and then we can get some serial data. The USB connector is shield is ground, so it's not supposed to touch anything. So now you can also see that when it comes down here, there's nothing short-circuiting here. So that's great. So let's see. It's probably supposed to do that. It's the L. The L. Okay. Not sure what the L is, but it's an Arduino. It's from Banggood. So when you download the source code from Jussi's website, you will get a VHDL file, which is the file for the CPLD, the one over there. So basically it's sort of a table of yeah, just logics really. It's seems to have one flip-flop there, but the rest is just simply logic. So glue logic, great. Anyhow, so wait, there was something about the LED there. LED out, let's see what that is. It's connected to enable, okay. Enable, okay, so enable is an input. So basically, whenever the CPLD, what shall I say? The CPLD is accessed, then it's activated. It's funny how you talk to the camera like you're filming and just took a picture. So it's the first time I'm programming, and I'm not that familiar with the Arduino. I know I have to put the Arduino file or Eno file into a folder with the same name for some reason, just the way it is, I think. And then you compile, just push it out, upload, and it compiled, but it doesn't find the board. What this means, I'm not sure. Attempt 4 not in sync, but I think it doesn't have connection. So it does say COM18, and but I think maybe it's this chip here, which is USB to serial, which is different, and you can also see it has been scratched off, the markings. So you have to install it somehow. So I'll check Banggood, the website, for driver. So this is the board I bought, and it's on Christmas sale. Seems like it's always on sale. It's really great. It has in EU also, because I don't think I've seen that before. Means you can get it really quick if you want one. I never had a normal Arduino. Arduino Uno is the normal one. So let's see if we can find some drivers. It says, I'm sorry guys, this version cannot compatible with all systems. Oh, and our driver is in Mother Russia, as you can see. It's funny how that installer looks like a crack, so just missing music here. But whatever works, so it's probably not a virus. So should I disconnect and reconnect? Yeah, maybe I should do that. Maybe it's easier to just go. Oh, by the way, I have a Christmas tree now. Let's check it out. It's on Barry's. Ingrid has bought this because the other one we had was very crooked. Yeah, I love it. This time it's LED lights, it's not those fluorescent type things. Or halogen it's called, maybe, I'm not sure. But yeah, ask Sir Clive, he does know. So lots of stuff. My sister gave me a shirt, Christmas sweater. She made it herself. I think it's cool. It's like a Christmas tree with presents on there and a little ribbon there. Yeah, I thought it was cool. And Ingrid has gone nuts with the Santas and then Santa Mouse and everything. So yeah. But this desk is my work desk, so only one Santa, maybe a little bird. I saw this bird on this Julian's channel. What is his name again? Julian. Anyway, he was from class also. I gave it to Ingrid in birthday gift, and you can see here also. I have a little. She got this one. It's a couple of years ago. It's just an RGB thing. I thought it was cute. So yeah. There's also very poor contact. Lots of candy. So for you who or you who don't, remember days of the before the internet. We had COM ports, physical serial ports actually. But now we have like a virtual one. So we can program as if it was a serial port. It's much easier than USB because USB is pain in the ass. There it is, so it's there. So why doesn't it work? Let's try it again. Probably this time it works. Wouldn't surprise me, but I should see some action going on here, but no. So am I supposed to hold the button?
Oh no. Gate?
Intermission. So I uninstalled the driver, unplugged the Arduino, installed the driver again, plugged in the Arduino, and then it worked. Typical Windows problem. Okay, so it didn't work. Why didn't it work? Well, I couldn't measure any 3.3 volt on this board. So what I did was I take 3.3 volt from the Arduino, which is under here, to the power connector, and then it works. But it's nowhere in the documentation where it says that you need a 3.3 volt source. So why this is, I can't answer, but I only think that it's coming in there, and the 3.3 volt, well, it's there, so it kind of looks like it's not connected, maybe. But in Eagle and KiCad, when you say 3v3, then it's connected to 3v3, but not in the schematic, I think. So it's kind of weird. Yeah. And you can see the power is VMAM, and VMAM is 3.3 volts. So yeah, so that's okay, but no 3.3 volt. I think the reason might be that maybe they think that the Arduino's 3.3 volt driver isn't hard enough. So this is the Arduino, and here is the 3.3 volt regulator, AMS 1117. So I can look that up. 1 ampere, well, if it's 1 ampere, then I don't want to even check how much this thing draws, because it doesn't draw that at all together with this, so I think it'll be fine. So what I will do when I test this is just hook 3.3 volt there to there. So I don't know why he has done that, but as usual, it goes to say just to check the voltages and everything's okay. Woohoo! Ho ho ho! Merry Christmas! So try talk over this video the best I can. I don't really like doing that. It's not so easy. It's like 31 minutes into the video also. But anyway, this is the Arduino, and it has been programmed, and here you can see what comes back from the Arduino. So it says, welcome, if you're new, try using the commands RWT blah blah blah. So I write the beef in hex, and you can see okay, I read because I had written that before. So I just write FFFF. Now we apply the magnet. Oops, attach. It wasn't supposed to attach. Read back. It's 0. So yeah. So basically, a magnet destroys data. So try it again. Magnet. Oops. Gunsky. Ooh. Now we write dead beef. See. Yeah, dead beef. A nice thing about dead beef is that it's easy to recognize in hex. It's like readable. So, but anyway, dead beef is gone. So let's write it in here. Let's try unplugging power. Oops. Here we go. turn off the Windows sounds. There you see, it's still there. Great. Dead beef. So yes, it's a non-volatile memory. And the magnet destroys it again. So yeah. Right, so now we're running the U test. So it means it just runs through and writes and reads a random over and over, like thousands of times. And then it reports on errors. So now it has run to 20,000 times and no errors. We hold the magnet next to it. Okay, this is fast forward actually. So you can see we had 17,000 errors. This is the T test, and that means write 0, read 0, write 1, read 1. So that seems to work okay for all addresses. Now I hold a magnet next to it. You can see some of the ones are now zeros instead. So wrote 1, read 0. Take the magnet away and everything's okay. So yeah, so hope you had a great Christmas. Bye bye.
ชูชูพายังมาทวนนะครับทวนออก